Hey, VSauce.
Wait, hold on. You can't say that.
Oh, shoot.
Think of something else.
VSauce. Michael here, and Uri and Cameron. And what's the smallest thing? A guy Democritus asked the same question way back in 400 BC. He had the idea that maybe tiny units called atoms composed everything in the universe.
After him, another guy, John Dalton, theorized that atoms were uniformly dense, solid masses, like billiard balls.
What say ye, Democritus?
Ye having a good time.
Following Dalton, a man by the name of J.J. Thomson discovered the electron and proposed a new model, affectionately named the plum pudding model.
Challenging this model, Ernest Rutherford proposed that the electrons orbit a central nucleus. However, this didn't explain the atomic spectrum. Then came along a student of Rutherford's named Niels Bohr, who came up with a commonly accepted Bohr model, displaying rings in which the electrons orbited at distances depending on their energy level.
While we have a good idea where an electron is located, we can really only be sure about the probability of an electron being in a certain region. Schrödinger found if you treat electrons as matter waves, the square of the wave function represents the probability of finding an electron in a given region within the atom.
The difference in the energy of energy levels is equal to the energy of the emitted photon, which are only found in multiples of the fundamental charge. These energy levels you will typically see labeled n equals 1, 2, 3, and so on. When a photon is absorbed by an electron, the electron will jump up to a higher energy level. We call this jumping up movement excitement. When an electron is excited, it gains potential energy, moving to a higher energy level. It then can fall back down to its original level through multiple paths. In this case, either from n equals 3 to n equals 1, or from 3 to 2, then 2 to 1.
There's a special case with hydrogen, where energy equals negative 13.6 over n squared electron volts, n squared being the number of the energy level. Take caution with this equation because it's only for hydrogen. So in other words, it'll trip you up on Mr. Beck's tests if you're not careful.
What is known as the photoelectric effect is the electron-emitting behavior of metals when they absorb photons. When the metal is connected to a battery, the voltage at which the current becomes zero, taking into account this effect, is called the stopping potential. To express the relationship between the wavelength of the photons and the amount of electrons emitted, we can use what is called a wave function, which takes into account the work function of the metal. The wave function can be graphed as a linear function on a coordinate plane where the y-axis is energy or Kmax and the x-axis is frequency, with the y-intercept being the negative of the work function and the slope being Planck's constant.
When a photon collides with an atom and is absorbed, and another photon is emitted, the atom will recoil in another direction. This means that photons must have momentum despite being massless. Lewis de Broglie devised a way to calculate the momentum of a photon using its wavelength and Planck's constant.
So I hope we've shed some photon light on quantum. And as always, thanks for watching.
Go.
Oh, let me do that. Okay.
Ready?
Hmm.